Hello, everyone. Glad to see you here. Just waiting for people to join in. Okay. Yes. So we'll begin in another minute. I think we are all set and ready. Okay. So let's see. Let's wait for a few of them to join in. Yeah. Uh, okay. Okay. So just probably in a minute's time, I think we should be able to start with this. Let me just quickly check if everyone's there, and we will begin. Okay, so we have a couple of viewers already joined in. Can you please text in who all are present so that we can begin the session? Yeah, I guess now you can see my screen. Uh, we are just waiting for people to really join in. Yes, so we are all set. Anyone who's present, can you just quickly let us know if you are there? Can you just text in your name? Yes. Okay, so yeah, is here. Anyone else who's joined in? Please type your name. Yeah, a few instructions. If you have any doubts, you can just post your doubts on the chat in the WhatsApp, or you can also post it in the YouTube channel. Yeah, and I should be able to respond to it. Please allow a small lag because your post generally comes while I've moved on the topic. But be assured that I'll get back to the topic and explain you whatever you are doubtful about. So anyone who is still there on the YouTube, can you just please post your name so that I am aware that you are there? Feel free to join in. Right, and. Yeah, let me just quickly check the screenwriter as we speak. Okay, so yeah, there we are. Yeah, perfect. I think everything is working fine. Sure. So let's begin. Now, so today, yeah, so Kritika is also here. Great, great guys. So let's begin. Now, sure. So people are joining in as and when they could really look up with the message. So today we are going to discuss and understand the summary on two chapters, not one. The first chapter we are going to see is acids, bases, and salts, and the second one that we are going to see is periodic classification of elements. Oh, that's fantastic. So Mehul is here, Anand is here. That's excellent. Anyone who joins in, please type in your name so I don't know that you all are present. Okay, good. So now let's begin with the presentation. Today we'll see in a quick look at both the chapters and try and understand the basic principles. We'll also try to look at how to write major answers and what points are important in a particular question when we are addressing the question in terms of acid, bases, and salts chapter. So To begin with, what are acids and bases? So when we say acids and bases, there are two things that we generally discuss. The first thing that we discuss is the property of acids and bases, and not the definition. Please note that acids and bases have three different definitions depending on how you are looking at, whether it's a solution or whether it is a electron exchange or whether it is simply a proton exchange. But so when we say what are acids and bases, the first thing that we talk about is its properties. So the properties that we are speaking here is all the acids. The very word acids comes from a car or asar, as you can pronounce it. Now, asar basically means that something that tastes sour in taste. Okay, so we know that acids are actually sour in taste. That's where the very name acid comes from. Uh, and bases are bitter in taste, right? So this is the first property of acids and bases. The second property is, of course, they change blue litmus into red, and they base changes red litmus into blue. Now, to remember this, there is a shortcut that you can always have is BRB. Be right back, as we write in chats. Now, BRB simply means that bases turn red litmus blue. So bases turn red litmus blue. Or the other way to remember this is all acids are dangerous. So acids always give red coloration. So these are multiple ways that you can actually remember the context of how acids and bases turn litmus paper. So anything that is comfortable for you, just remember the color. That red is litmus turns blue in bases and blue litmus turns red in acids. Now, what are examples of typical acids? Hydrochloric acid is one example of acid. Sulfuric acid, nitric acid, acetic acid. Similarly, if you really look at bases, you'll find the examples as NaOH, KOH, very strong bases. Calcium hydroxide is another base. Ammonium hydroxide is one another base. Now, before we really go forward, I'm going to tell you the flow of this chapter. So the chapter really starts with definition and properties. Okay. The second thing, let me use a better color. Probably the marker is not that good. Okay. Yeah, so this is maybe could be written pretty well. So the first one is the definition and properties is what we'll be looking at. The second one that we'll look at is what are the different types of classifications of acids and bases, and how can acids and bases be looked at from different perspective. So classification is the second topic that we have to really look into. The third one here we will find is what is a pH. Okay, and then the fourth one that's very important that we can really look at uh, is basically the the last one is where we have some important chemicals that we have to really work with. Okay, and there are 6 important chemicals that we work with. So all of them put together, we will understand the properties, methods of preparation, etc. So there are basically these 4 major points of this chapter which we'll be looking forward as we study this chapter. Now let's go to the next page, and we find that these are some common acids that are there around our house or in our daily use. Now, what are those common ones? Basically, HCl. HCl is what is present in our stomach. The pH of our stomach is not that acidic. It's fairly acidic, you can say. The acid refluxes that we get, and when we find a burning sensation in the throat, that's when HCl is too much. It's become too much HCl in our stomach, which is basically coming to our throat. The second one you have is sulfuric acid. So sulfuric acid is something that you find in car batteries, pretty common in the household, especially in these days where there are a lot of power cuts. So we know that sulfuric acid is what we use in the batteries, not just car batteries, but also in household. There is a lot of sulfuric acid that we generally use around. So that's H2SO4. Then we have nitric acid. Nitrogen is involved in making a lot of explosives. For example, trinitrotoluene, RDX. So in all of these substances, nitrogen is a very, very important component, and that's where nitric acid is utilized efficiently, and it's present all the time. The last one is acetic acid. Acetic acid is basically CH3COOH. Now, if you see, it is we have written this in a very typical manner where we have written H at the beginning, and then CH3COO we have written as C2H3O2. Please do not get confused by the name. This is nothing but the same acetic acid, and I'll try and explain why this actually turns out to be the same. Is basically CH3COOH. The H is the only one which actually dissociates as H plus, and keeping the anion behind. This entire anion can be written as C2H3 and O2, right? And that therefore this is written as something like in the HA format, where HA, we have an H plus and an A minus, connecting us. So that's a quick look at acetic acid. The next one is carbonic acid, which is our sodas. So this is nothing but CO2 dissolved in water. So if you really add CO2 to water, you realize that the formula turns out to be H2CO3. And this is especially the one that we drink in aerated drinks, whether it is soda or your Pepsi's, Thumbs Up, any aerated drink, mostly would contain a CO2 compound, and which would be a carbonic acid, or H2CO3. So, and that's the reason when we have aerated drinks, the acidity, people who have acidic, refluxes a lot, will have their stomachs filled with acids, and sometimes is problematic. The last one is phosphoric acid that we see again around our house, mostly used in flavors, flavors of the households, wherever we use flavors. Great. So there are a few more students who have joined in. Param is here, Brian is here. So nice to have you guys. And let's continue with our revision forward. Some other common acids that we find in and around our houses is citric acid, which is present in the oranges, lemon. Both of them contain citric acid. Tartaric acid is what we have in our tamarinds. Oxalic acid is in tomato, whereas lactic acid is a common ingredient of curd. This is also one of the reasons why baking soda is added to pure milk, so as to neutralize the incoming lactic acid. So because milk contains lactose, which actually breaks down into lactic acid as curdling happens. The next one is of course formic acid. Whenever an ant or a sting that you get from these small wasps or some insects, most of them actually have formic acid in their sting, which is what burns. The skin that when we have a burn in our skin, that's where the sting is working with methanoic acid, which is also called as formic acid. The formula for formic acid is HCOOH. Now, this is the normal way of writing it. In the HA format, we can as well write this as HHCO2. Okay, this is how we write it in the HA format. HA format is basically an anion, A minus, with a hydrogen H plus. Okay, so that's a quick way of looking at all the acids that we know of. Let's look at common bases now. Yeah. So just a quick second. I'm just checking on the recordings. I hope everything is clean. Yes, it's all fine. Now let's look at the common bases that we have. The common bases that we really see around our houses is NaOH, which is not directly present, but these salts of NaOH is present in soaps, as well as in drain cleaner. MgOH, this is your magnesium hydroxide, is present in all antacids. So whenever we have acid refluxes, the antacids that we generally have either has a magnesium hydroxide, or sometimes you also do use sodium, basically sodium bicarbonate, which is your baking soda. That also helps in some ways. Now, another base that is commonly present in deodorants, is aluminum hydroxide. And of course, ammonia, which is present in most of the cleaning substances in our house, contains ammonium water, or ammonia water, or what we also call as ammonium hydroxide. So these are some common bases that we find around our houses. Now, as we discussed the first part, now that we have known what are acids and bases and looked at some of their examples, we are going to look at how are acids and bases classified. And there are multiple ways that you can classify acids and bases, right? Firstly, mostly the acids are classified based on their origin. So acids generally are either a strong acid or based on their origin, they're either an organic acid, or they are a mineral acid. Now, an organic acid basically are all those acids that are derived from plants and animals, or any living organism. That's the word organic comes from. For example, citric acid is derived from fruits. Acetic acid is present in vinegar. Oxalic acid is present in tomato. Similarly, you see tartaric acid present in tamarind, lactic acid in milk. All of these are examples of acids coming out of plants and animals, and they are the ones that are called as organic acids. Whereas if you see mineral acids, they are mostly inorganic. Inorganic means we would find them in Earth's surface, we would find them in the atmosphere, but they are not directly produced inside the organisms. They could be a byproduct of the chemicals that the organisms do have, but not directly produced from the living organisms. Now, what are these mineral acids? Sulfuric acid is a very well-known mineral acid. So it comes from the non-metal sulfur, which is again commonly found inside Earth in the acid format. So H2SO4 is a derivative of sulfur, and that's one of the typical mineral acids. Similarly, HCl is a derivative of chlorine, chlorine gas, if you might say, and that's also another mineral acid. So this is the definition of all the, or this is the classification rather, of all the acids based on their origin. Now, if you look at the bases, bases generally, and I would say even acids, they can be classified based on their strengths. And what would be a typical strong acid is nothing but those which completely dissociate. Now, please note, this dissociation is a phenomenon which involves breakage of bonds. Someone who is highly ionic, like KOH, NOH, they mostly completely dissociate in aqueous solutions. That means in water. So strong bases are all of those bases who give complete NaOH. So if you really write NaOH, and let's say you have taken n moles of NaOH, you'll find that it will end up giving n moles of OH minus. So whatever moles of NaOH came in completely dissociates into the moles of OH minus. So that's the typical property of a strong base. And what is a weak base is that weak bases do not decompose completely. So if you take n moles of a weak base, you'll find that the moles of OH minus that come out are pretty low. They would be very less than n. So n would be very large, and let's say we call that as n dash. The moles of OH minus would be very smaller as compared to n. Now, a typical example of a weak base is NH4OH, ammonium hydroxide. And a typical examples of strong bases are NaOH and KOH. In the same way, we also have strong acids. So strong acids would be, a typical strong acid would be your HCl, H2SO4. All these are pretty strong acids. So if you put all of these in aqueous solutions, you'll find that the entire H plus will come out. Please note, H2SO4 gives 2 parts per part of H2SO4, which means that every molecule of H2SO4 is going to give 2 H plus ions. So they would be giving out H plus, as they dissociate. So that's the strong acid examples. And then you have weak acids, which is a typical weak acid would be a CH3COOH. Also you have CH2COOH, and another CH2COOH. So these examples are pretty common. Oxalic acid. Now they would not dissociate completely. So if you take 1 mole of CH3COOH, you would hardly get about 0.0001 moles of H plus. So 10 to the power minus 2, 10 to the power minus 3, sometimes as low as 10 to the power minus 5. So that's the way that weak acids behave. So these are classifications based on strength. So we have seen 2 classifications so far based on the origin, and the second classification is based on the strength. Now let's look at let's look at the next uh, uh, yeah, just a second. Okay. Yeah, let me just, yeah. Now let's look at the second way, different classifications that are possible. So you will find that the next classifications are based on their concentration. Now we have seen strong acid and weak acid. The strong acid and weak acids and concentrated and dilute acids are something that they are not related. Sometimes people have a notion that if I take a very concentrated solution of CH3COOH, it will become strong from weak. That's not true. I find students having a lot of this misconception. the concentration has nothing to do. I mean, it does have to do, but only in one particular case, which we will discuss in a minute. But concentration per se does not have directly to deal with whether it's a strong acid or a weak acid. The only point of discussion here would be that if it is a very, very dilute solution, which means that if you just put about, let's say, zero point 0.1 moles of CH3COOH probably in 2, 3, or maybe 5 liters of water, so the concentration is going to be very low. In such circumstances, you'll find that the entire CH3COOH dissociates. This is technically also called as infinite dilution. But apart from that, you'll find that the weak acid and strong acid behavior of acids and bases is retained in most of the concentrations. Now, how do we really classify based on concentration is basically as dilute acids and as concentrated acids. Okay. Now, dilute acids have low concentrations of acids in aqueous solutions, obviously, and concentrated acids have high concentration of acids in aqueous solutions. Now, this is the classification based on concentration. Now, let's understand what's the next classification of acids based on the number of hydrogen ions. So if you really see, based on hydrogen ions, you have monoprotic, which means that you're just going to give one hydrogen atom, hydrogen ion rather. Diprotic means you'll be giving two hydrogen ions. Triprotic means three. Polyprotic means four. Now, to your surprise, there is another name for all of these, and acids are classified as basic, monobasic or so. So monoprotic also sometimes are called as monobasic acids. Why monobasic acids? Is because every acid of this type, which is, let's say, HCl or HNO3, is going to neutralize every base having one NaOH, or one OH minus rather. Okay, so HCl neutralizes one OH minus, and therefore monoprotic acids are sometimes also called as monobasic acids. Please note, it's again something that we might get confused with. Monobasic acids, I mean, acids are monobasic or dibasic or tribasic. They are not monoacidic. Okay, bases are monoacidic, diacidic, or triacidic. So monoprotic acids are also, in other sense, essentially, let me use a different color. Yeah, they are. We can write them as basic acids. Okay. Yeah, so that's one classification. Similarly, you'll find that we have dibasic. So H2SO4 is our dibasic acid, and similarly, triprotic or tribasic acid is H3PO3. Okay. Now, anyone who gives more than 3 H plus would be a polyprotic acid. Now, similarly, as we have seen H plus, we'll also see OH minus classifications. So you'll find that in OH minus, monoacidic base is basically someone who gives only one OH minus. Now, please again note that being monoacidic or diacidic does not mean that you're strong or weak. There is no correlation. You might have monoacidic bases. Let me look at an example. Yeah, so I think the least would be, although that's also a fairly strong base, but the least would be maybe LiOH. Okay, so it's monoacidic, but it is still weaker than, for example, bases like NaOH and KOH. Whereas dibasic would be CaOH twice, and tribasic are AlOH thrice. So the point that I'm trying to make is, most of the times you'll find that yes, the monobasic ones might be slightly stronger than dibasic, but there's not a one correlationship. So strong and weak are to do with how much you dissociate, whereas monoacidic, diacidic are to do with how many OH minus you provide as you dissociate. Okay, so that's a quick look at all the classifications. Now, the next is to understand how do we really have uh, how do we really know whether something is an acid or a base, and that's where indicators comes to our help, pretty much, right? So you'll find that indicators are all of those who actually help us in understanding what an acid or base is. So it indicates the presence of an acid and base in a solution. Now, let's look at how litmus works. We have already seen that in the definition, but litmus is a very natural indicator and it's very commonly used. It is a purple, day extracted from leachins, basically. It's a chemical being extracted from leachins. Now, some other examples of indicators would be red cabbage, colored petals of Putinea, and turmeric. They show coloration in acid differently and in base differently. We know of litmus very well. Litmus actually becomes red in acids, and it becomes blue in bases, right? So yeah, so that's the coloration of litmus. Now, there are a few others which also show, indication, which is our, through smells. Also, we can understand whether something is an acidic or basic. Olfactory indicators are, for example, onion. Onion gives a very typical smell. So we know that onion is basically acidic in nature. Similarly, clove gives a very typical smell. Again, there is acid present in it. So based on the smell, also you will be able to understand whether something is acidic or basic. So these are all olfactory indicators of acids and bases. Now let's look at the most common color changes. If you really look at the red litmus, we have seen red litmus just a minute ago, that it changes to red in acids, and it changes to base. So blue will remain blue and red will remain red in acid. If you really look at turmeric in acids, it has no change. But in base it actually turns red. Okay, so this is very surprising. It's exactly opposite to that of litmus coloration. In bases it is red. If you really look at methyl orange, you'll find that it shows the coloration very similar to litmus paper, which is red in methyl orange, and it is actually yellow in a base. Okay, so you can always put a base and test whether methyl orange is in yellow coloration or not. And phenolphthalein, which is also very commonly used, there have been many multiple questions asked, especially on these two indicators. Now, phenolphthalein is generally colorless in, if you take a phenolphthalein bottle, which is in the pure form or maybe in the diluted form. But as soon as it touches acid, you'll find that the colorless remains colorless, but it becomes pink in base. Okay, so what was in acid colorless, it turns to pink as you go to the basic side. So these are the different colors that we just spoke about, and which would help you to understand whether something is acid or base. Now we are going to look at all the chemical properties of acids and bases, and there are roughly about five reactions for acids and about three reactions for bases. Primarily, that has been discussed in the textbook, which we are going to really look at. So the most important reaction that we have with acids is when metals are put in acids. So essentially you end up getting salt plus hydrogen. And the common test to recognize hydrogen is to have a pop test. Okay, what does a pop test basically mean is that the hydrogen gas that is released as a product of uh, let me just yeah as a product of the reaction. If you use a burning candle around this hydrogen gas, near the test tube, you'll realize that a small pop sound is heard. This is because of explosive burning or combustion of hydrogen, as you keep the burning flame very close to the test tube. So this test is generally conducted to know whether hydrogen is getting released or not. You can also refer to the activity that's on page 19 of the NCERT book to really understand this topic pretty well. So these are the different examples what a typical metal would do with an acid. So if you really have HCl put with zinc, you'll find that H2 is released. So this H2 gas is given out as zinc reacts with HCl. Yeah, yes, there it is. And then we just a second. Let me also use. I'm going to try to use uh, pen transparency. Okay, let me just use. Okay, yeah, now we are good. Okay, this is still not working out. Give me a second, guys. Yeah, I'm just trying to use a better. Yeah, there it is. Yeah. So now, okay, and we are ready. Yes. So I was saying that the H2 gas is released as we really speak about zinc being put into an acid. Similarly, zinc is put with HNO3. You realize that another H2 gas is being released here. Similarly, zinc with H2SO4, and the last one is zinc even with a weak acid will give out the hydrogen gas. So all of these gases are released, and that's what we have the pop sound coming out from. So this is a quick reaction of acids with metals. Now let's look at bases with metals, and you'll find that bases with metals actually give hydrogen as well. But this note, please, this is one of the most important point, is that note these reactions are not possible with all the all the metals, only zinc essentially gives out this particular reaction. So you end up forming sodium zincate, and hydrogen gas is released. But other metals may not give this. The other example that is very typical is to use aluminium. Okay, so aluminium also ends up giving sodium aluminate, which is another metal which actually gives hydrogen gas in presence of bases. But again, these are few and far in between. So therefore, this is one typical reaction which can help you identify a certain amount of metals, when they're put with bases. So that's the reaction for acids and bases with metals. The next reaction is acids and bases with carbonates and bicarbonates. Okay. So what are carbonates? Carbonates are something that has a CO3 2 minus ion in it, an ion present in it, and bicarbonate is something that has HCO3 minus an ion present in it. So both of these actually end up giving you CO2 at the end of the reaction. Now, a typical reaction is mentioned below. So you will find that whenever you have a metal bicarbonate with acid, it will end up giving salt plus sodium, carbon dioxide plus water. So CO2 plus H2O and NaCl pretty much is given out. When you have a carbonate, which is Na2CO3, you will find that Na2CO3 reacts with HCl, and you will find that the salt plus water plus CO2 is given out. A quick note here again, anytime you feel that there's something that you need to ask up, you can always put in the comments, either mostly at the Yahoo, sorry, at the YouTube chat, and I will be able to answer those queries. So the reactions of carbonates and bicarbonates both give CO2 and H2O. The only difference is that you'll find that in carbonates you will find 2 moles of salt coming out, whereas in bicarbonate only 1 mole of salt is given out. So that's the the reactions of acids with carbonates and metal bicarbonates. Now, the next important reaction that we need to know about acids and bases is, most of the bases, whenever they release, whenever CO2 is added to them, you'll find that they end up giving out a white precipitate, which is nothing but a carbonate that is precipitated. Okay, so this is a very good test to have to know bases present in aqueous forms as such. So you'll find that CO2 gas, when it is bubbled through lime water actually ends up giving white precipitate. But if we keep on passing excess of CO2 for a very long time, this milkiness again disappears, and that is because of formation of bicarbonate. So carbonate is actually a white precipitate, but bicarbonate is soluble in water, and hence whatever white precipitate we had when we passed the CO2 for the first time, slowly disappears as more and more CO2 is passed through the entire solution. Yeah, I can see a few more joining in, Anirudh and Shreyas. Yeah, that's good, nice. Feel free to stay connected and ask questions if you have any. Okay, so that's the carbonate and bicarbonate test that we have for CO2 especially. Now let's look at the neutralization reaction, which both acids and bases definitely show, because it is actually a reaction between acids and bases. So you'll find that whenever an acid and base is reacted together, you'll end up getting a salt and water. This reaction is pretty well known across the board now. We have NaOH plus HCl giving NaCl plus H2O. Maybe I'll take a very odd example of CH3COOH plus, let's say, NH4 OH, which is basically acetic acid plus ammonia water or ammonium hydroxide. You'll find that this is an acid and this is a base. When acid and base react, you'll end up getting a salt, which is a very typical salt of ammonium acetate. Okay, so this is CH3CO minus NH4 plus. This is the salt that you end up getting, and obviously a water is given out. So every acid and base, just simply take out the H plus and OH minus from the acid and base respectively, and you'll end up getting a salt plus water. So this is a quick look at the acid base reaction of neutralization. The next reaction is metal oxides reacting with acids. Now just I'm for everybody's clarity, please note that all metal oxides and all metal hydroxides are basic in nature. So metal oxides, metal hydroxides, just with the exception of copper, zinc, and aluminium in our syllabus, which are actually amphoteric in nature. So copper oxide, zinc oxide, and Al2O3 is amphoteric. Amphoteric means acidic and basic both at the same point of time. So they will behave depending on who is reacting with them. So these three are amphoteric in nature. Apart from them, most of them, all the metals would be basic. All metal oxides would be basic, and all metal hydroxides. All of these are basic in nature. But if you look at acids, all the non-metals are acidic. All the non-metal oxides, are acidic, and all the non-metal hydroxides are also acidic in nature. Let me give you an example. For example, chlorine Cl2 gas is pretty much acidic. They would take in the electron from anyone, and would be happy to form HCl kind of compound. So they're acidic in nature. Non-metal oxides like CO2, whenever they dissolve in water, they end up giving H2CO3, which is again an acid. Similarly, non-metal hydroxide, which is nothing but H3PO3. So H3PO3, phosphorus acid is basically POH thrice. So POH thrice is again basic in nature. So non-metal oxide, and non-metal hydroxides are all basic in nature, and so on and so forth. So now let's look at what metal oxides will do with acids. Because metal oxides are basic, obviously their reaction with acid is more or less symmetrical to the reaction of neutralization reactions. So this is a base, except without an OH minus per se. But at the same time, this is a base as per one of the definitions of bases, that is the Lewis definition. So CuO is the copper oxide, HCl is the hydrochloric acid, and they both actually end up forming this salt, which is nothing but copper chloride, and of course water. So an acid plus this is our acid here today, and this is the base. They both react to end up getting salt and water, which we have also seen in the neutralization reaction. So that's a typical metal oxide plus acid reaction. And you'll realize that as this reaction goes forward, the appearance of the blue-green color of the solution comes up because of the formation of CuCl2. So this is the one that is of bluish greenish color. Okay. Yeah. And also what happens is that as we have mentioned that all metal oxides are bases, basic, and therefore they're basic oxides. They end up giving salt and water as they react. Okay, good. So this is the reaction of metal oxides per se. Now let's go to the next reaction, which is non-metal oxide with bases. We just saw that non-metal oxides are acidic in nature, like CO2, and therefore non-metal oxides will have a very good reactivity with a base. So if you really look at CO2, CO2 is nothing but water with H2CO3 deprived of water. Okay, so this is sometimes also called as dehydrated H2CO3. So COH twice, which is our calcium hydroxide, which is our base, actually ends up reacting with our acid, which is a non-metal oxide, and they end up giving us a salt, which is CaCO3, and water. Okay. So you end up having another neutralization reaction. The only difference is here we are not taking the acid directly, but we are taking the oxide of non-metal, which is by nature acidic, but not in the typical category of H plus donating acids. So non-metal oxides are said to be acidic in nature because on reacting with base they produce salt and water. Okay, so that's the reaction that we have for base as well. So that completes all our reactions. A quick recap at the reaction so that we have this at the top of our mind is that we have the following reactions. Firstly, we saw metal reacting with acid and metal reacting with base. These are the two reactions, important ones. Hydrogen is always given out. The second reaction, we saw that metals reacting with carbonates and bicarbonates. In both of them, metal carbonates and bicarbonates reacting with acids. In both these situations, CO2 is given out. Then we saw, how do we really test whether CO2 is given out or not. The CO2 that comes out of this acid and carbonate reaction is fed to the lime water, and you will find that the lime water actually ends up giving white coloration, that is milkiness, and the milkiness further disappears as the carbonate turns to bicarbonate, which is soluble in water. Then we saw the neutralization reaction given again by base and acid. In this reaction, a base is used as a testing mechanism, whereas the acid is used as a reacting reagent. And the last reaction we saw was of oxides of both metal and non-metal oxides with the counterpart, right? So metal oxides with acids and non-metal oxides with bases, because metal oxides are basic in nature and non-metal oxides are acidic in nature. Right. So that's a good view of all the chemical reactions that acids and bases give. Now let's understand the strength aspect of acids and bases in slight more depth. So the strength of an acid and base basically is given by a factor, or by a parameter called as pH. The P comes from potens, which in German language or Deutsch language means power. So pH means the potens of hydrogen, which means the power of hydrogen. Now, the strength of acids and bases actually depends on the number of H plus ions given out. Uh, yeah, so the number of H plus ions given out by acids and number of OH minus given out by bases. So if acids are giving out too many H plus ions, obviously it is going to be stronger, and if bases are giving too many OH minus, that's also going to be a stronger base. Now, how do we really understand whether too many H plus or OH minus are not are given or not? So we use something called as an universal indicator to find the strength of acids and bases. Okay. Now this indicator is also called as a pH scale. Okay. Now the universal indicator actually ends up giving out a lot of uh, a scale. The scale for knowing what really is the strength of an acid or base. It From its coloration, we understand whether something is really acidic or basic or not, right? So how does the scale really measure? The scale starts from 0, which is very acidic, and it actually ends up at 14, which is very alkaline, and 7 is what we consider as neutral. Please note this is neutral only for pure water. Okay, so whenever you have a pure water, you find that the pH would be somewhere around 7. Now, one more definition of pH is is given by pH is equal to actually minus log of the H plus ion concentration. So this is also the definition of pH value. So how many H are given per unit per liter of the solution? You'll find that that is the concentration of H plus, which when fed into this formula, we end up getting the value of pH. Okay, so this is the mathematical formulation of pH, but practically we understand whether something is very acidic or basic depending on the universal indicator. And if universal indicator shows very acidic substance, then we know that the pH is somewhere equal to 0, whereas very alkaline is somewhere equal to 14. Now, there is also a pH paper that we use for measuring pH, and those colorations actually will end up giving us uh, the understanding of whether something is very acidic or basic or not. Okay, now let's look at the strength in some more detail. Here is the coloration of a pH paper. As we discussed. You'll find that the pH paper will give these colors as dark red if it is absolutely acidic, and the pH coloration actually increases to dark blue or violet as it becomes absolutely basic, which is 14. Right now, if you really see, this is a coloration which is very similar to Vibgyor. Okay, so Vibgyor is our colors in the rainbow. So violet, indigo, blue, green, yellow, orange, and red. So you'll find that dark red is where we find the acidic scale. So acids would on the universal indicator or the pH paper would be absolutely reddish, whereas dark blue or violet, the indigo spectrum is very much for bases. And you'll find that in between there is green and there is yellow and orange. So remember, red is for acids, and this is also the coloration which we saw with litmus paper. So that will also give you an idea of how to remember the colors. So for litmus, we had red for acids. In universal indicator also, acids are given by red coloration, whereas bases given by violet or blue. Okay, so that's the way to understand the pH values of acids and bases. Some examples of very strong acids are HCl, H2SO4, HNO3. Some examples of weak acids is CS3COH and H2CO3. Examples of strong bases: NaOH, KOH, CaOH twice, whereas example of weak bases NH4OH. So yeah, so these are the ways to understand weak as the strength of an acid or a base, through the pH values or through a pH paper or universal indicator. Now, okay, so now let's look at what is the importance of this pH. Why are we studying the strength of acids and bases? What's the reason that we need to understand acids and bases as such? So the importance of pH in our daily life is the following. Okay, so you'll find that the one of the most important things of knowing pH is actually to understand our digestive system. Okay, so pH of our body is regulated very effectively by our blood, but at the same time our body also regulates the pH in our digestive system. Whenever we have an indigestion, the stomach basically has produced more of acid, and this acid is why we get acid refluxes, which we have been mentioning since the beginning of this session today. Also, you'll realize that if you need to get relief out of these acids, we actually need to have some antacids used. So as we use more of antacids, the acid is neutralized, and our acid refluxes stop. So antacids, which is our magnesium hydroxide, sometimes even small amount of baking soda, which is basically used in eno as such, is so that's one. Then therefore we need to know what is exactly pH of our digestive system, and should we inject more of acidic substances or not inside the stomach. The other major importance of pH in our daily life is our acid rain. So because of the pollutants that we have been putting out in the atmosphere, in fact, to your surprise, this year in the JEE mains, IIT JEE mains for the 12th graders, there was a question which asked what is the pH of rainwater in or acid rains, and there were options given as 5.6, 5.8. So this was a question that was directly taken from the 10th standard textbook. This shows how much of the information that's given in NCRT is important for us to understand and remember. So if we have done our 10th grade syllabus as well, the students would have attempted the question very well in even the JEE mains. So pH of acid rain is basically somewhere around 5.6, and since it is on the acidic side, we call it as acid rain. These are mostly non-metal oxides like CO2, SO2, NO2 being released inside, in the atmosphere, which ends up forming H2CO3, H2SO3, HNO3, so on and so forth. Yeah, and that's why we call it as acidic rains. Now obviously metal oxides are not gaseous enough to actually have presence in the atmosphere, and therefore we do not have basic rain for that matter, right? So we only have heard of acidic rain, but this possesses a lot of threat to the human life because it corrodes our metals, it corrodes a lot of systems that we have, and also is harmful for our human body. The Yeah. Yeah. The next is understanding pH of soil. So pH of soil is basically something to be known in agriculture, or whenever we plant trees and saplings and any vegetation. Now if the pH is not within the range suitable for the particular vegetation, we'll find that the vegetation will not survive, and therefore farmers keep on adding fertilizers, or keep on adding different kinds of additional substances, especially buffer substances, which can maintain the pH for a particular soil and vegetation type. Now, again, our body functions. Basically, this is the blood that we are talking about. Blood is quite alkaline, and therefore our body really functions in term, between 7 to 7.8 pH range, and therefore this pH range is where most of the living organisms can also survive. Only and therefore it's very essential for the body to maintain the pH within this range. Okay. Now the next is the tooth. Now whenever there is bacteria present in the tooth, it produces acids. By the degradation of sugar and food particles. Unfortunately, the gaps here is suddenly gone because of the projection. But the point is that these bacteria keep on producing acids, which keep on decomposing the calcium inside the tooth. So we use toothpaste, which is mostly basic in nature. So most of our toothpaste, especially the natural toothpaste like Colgate and all that we use, are mostly basic, which neutralizes the excess acid and prevents tooth decay. Then the next thing is, we also have bee stings or nettle stings, which contains formic acid and causes pain and irritation for us. If we use a weak base like baking soda, it gives us some relief because it neutralizes the acidic content of the bite, and things remain pretty simple. Now, uh, okay, so this is the importance of the acids, the pH in our daily life. And yeah. Now let's understand the different types of salt. So we have seen what are acids, what are bases. Uh, there are also similarly the types of salts. So there are neutral salts, acidic salts, or basic salts. Essentially, this acidicity, basicity, or neutrality of salts comes from what will be the aqueous solution of that particular salt when we dissolve these salts in water. Okay. So if you, for example, take acidic salts, they are made up of strong acids and weak bases. So if you really put this inside an aqueous solution, you'll find that the strong acids would actually dissociate completely, giving a lot of H plus. But the weak base that will be formed, if you hydrolyze this, will not end up giving complete OH minus. So there will be more amount of H plus that comes from, for example, NH4Cl. The Cl minus will take in a lot of H plus from water, but NH4 will not be able to produce so much of OH minus, and therefore whomsoever is stronger will exhibit its strength inside the aqueous solution, and you will find that this salt will become an acidic salt. Similarly, there is a basic salt where the strong base that gets strong base and weak acid is what will form this salt. So in this situation, you can see that CaOH twice is a strong base, but H2CO3 is a weak acid. Similarly, our CS3CO minus is a weak acid and NaOH is a strong base. So when they are dissolved in water, the water will be mostly alkaline in nature. A quick question for a quick bit of information for you. The difference between alkali and a base is that alkalis are mostly soluble and they are group 1 or group 2 element hydroxides. Also, most of the alkalis will be OH minus donators, whereas bases are in general, all types of bases would be with OH or without OH minus. For example, ammonia is a base which does not give any OH, but it is basic in nature. But we might not call ammonia as alkaline because alkali, because for the reason that it is not a group 1 or group 2 element, although ammonia is also soluble inside water. But alkali typically is called for all those bases which are firstly soluble in water and are made up of group 1 and group 2 element hydroxides. Okay, so these are the types of salts that we have seen after seeing acids and bases. Now the yeah now moving on is the last part of this chapter, where we would need to understand major 6 compounds, and those 6 compounds are sodium hydroxide, gypsum, plaster of Paris, bleaching powder, baking soda, washing soda, all of those. So we are going to see all of these 6 compounds one by one, and what are the important points on all of these 6 compounds that you need to remember before heading for the exam. When we talk about sodium hydroxide, we actually the first thing that we our textbook actually discusses is its preparation method. Now, sodium hydroxide is prepared by a method called as chloralkali method. Chloralkali because we end up getting chlorine as well as a base, which is NaOH, and therefore it is a chloralkali method. The name itself means that chlorine and alkali is being given out. Now, what is this method? Is basically you are using a brine water. Brine water is NaCl or salt dissolved in water, and we basically what we try and do is we electrolyze this solution. So therefore, the electrolysis ends up giving us NaOH, Cl2, and H2. H2 is given out at cathode, which is the negative electrode. So electrons are taken up by hydrogen, and hydrogen gas is released. Whereas chlorine is given out at anode. So chlorine donates the electrons at anode and is liberated. But in the solution from water, a lot of OH minus remains, whereas from Cl2 is given out. So therefore, there is a lot of Na that is remaining from NaCl. So NaOH keeps on getting concentrated inside the solution, and after some point of time, we find that there is a lot of amount of NaOH in the aqueous solution, and therefore the solution becomes very basic. Now, what are the uses of sodium hydroxide? Mostly, this is used in most of the laboratory, equipment, most of the laboratory preparations. Apart from this, it is used in multiple industrial processes as well. For example, basic hydrolysis of polymerization. So, whenever you want to make polymers, for example, our rubber, nylon, all of these are polymers. Basic and acidic hydrolysis both are used. whenever we need a basic hydrolysis to be done, NaOH is a very handy substitute that we generally use. So this is a very useful base, and is prepared from electrolysis of brine water, as we have seen just now. The next element that we need to see is bleaching powder. So from the very word bleaching powder, we know that it gives us bleaching action. Now bleaching action basically means that uh, we are putting up something that is going to corrode the color of the substance, or is going to oxidize the substance heavily. So you'll realize that CaOH twice, when it is passed, when chlorine gas is passed through it heavily, we end up getting CaOCl2, which is what we call as the bleach in water. And when bleach is present in water, the solution is called as bleaching powder. Now this is nothing but what calcium hydroxide chlorine. That's the name of the uh, the compound bleach, the official name, or the scientific name of the compound bleach. Now this bleaching powder is used to bleach water as well, so it very much purifies water, because it oxidizes any impurities in it, and then the impurities either can be filtered out, or simply are given out as gases. Then it's also used in the bleaching powder. This is not power but powder. Okay, so bleaching powder also is quite common. Bleaching powder is used to clean utensils. It is used to clean the restrooms, the washrooms, the tiles, the flooring. Also bleaching powder is used in textile, in factories, in laundry. It's pretty much available as disinfectant as well. So there are a lot of uses, and there are a few uses given in the textbook that I've already mentioned in here. So remember the uses of bleaching powder as well as its preparation method, mentioned to you in short here, as on the slide. The next is baking soda. So baking soda is nothing but sodium bicarbonate. Now, whether it is a preparation of sodium carbonate or bicarbonate, both of them come from the same process. And this process we typically call as the Solvay's process, where NaCl plus H2O plus CO2 plus ammonia, four ingredients are used in the end to give out ammonium chloride and sodium bicarbonate. And if we keep on heating sodium bicarbonate, we end up getting sodium carbonate, right? So plus water plus CO2. So the Solvay process, this is called as also, other name is called as the Solvay process, is also used to make not only sodium bicarbonate but also sodium carbonate. Now, in most of these situations, whenever we use baking soda, a lot of CO2 is released. So this CO2 produced thus is used for any dough to rise, because it basically bubbles out of the dough, and helps it make very spongy and crispy. So therefore it is also used in preparation of bakery items, which is like cakes or pastries, and also to make them quite spongy. What are the other uses of sodium bicarbonate or baking soda? We use as antacid. I already mentioned to you. Very similar to MgOH twice, it is also used as antacid. It's also used in making baking powder, which we are aware of. On heating baking powder, it ends up producing sodium salt, as well as sodium salt of acid, as well as the CO2. So these are different uh, yeah, so this is a different uses of baking soda that we have, and I've just mentioned shortly in this for your convenience. Now let's go to understand the next compound, which is washing soda. Now in washing soda, you will find that uh, uh, the only difference between baking soda and washing soda is of a hydrogen. Washing soda is sodium bicarbonate. Sorry, baking soda is sodium bicarbonate, whereas washing soda is sodium carbonate, which is Na2CO3. Now, when we actually have Na2CO3, put in water, we end up getting Na2CO3 10H2O, which is basically the water of crystallization with washing soda. This is what is in the end called as washing soda. So sodium carbonate in itself is not washing soda, but Na2CO3 10H2O is what basically is washing soda. We already seen its preparation in the previous process. Its uses are used in glass, used in soap, used in paper industry. It's also used as cleaning agent for domestic purposes, because it removes the hardness of water as well. And it's also used in the manufacture of borax. Borax is basically B2 so B2O3, So that's so basically boron oxide. Okay. So borax is something that's also useful in cleaning and cleansing actions at household and in industry. So that's a typical usage of washing soda. Let's look at the next chemical, which is gypsum and plaster of Paris in the same instance. So if you really look at gypsum and plaster of Paris, they only differ from each other by some units of H2O. To be precise, they differ by 1.5 unit of or 1.5 mole of H2SO4 per mole of gypsum as per mole of plaster of Paris. Now, if you really see, copper, plaster of gypsum and plaster of Paris are both uh, calcium sulfates. Now, this calcium sulfates can basically be obtained directly from the Earth's surface, like from ores like dolomite and all. So the formula for gypsum is CaSO4 twice of H2O, and the on heating gypsum, at a very high temperature, almost at 100 degrees Celsius, we end up getting plaster of Paris. So it loses its water of crystallization and it hardens up. So as it hardens up, you will find that plaster of Paris is produced. Plaster of Paris is easily moldable, and it also, becomes harder and stronger as soon as the water is excess of water is evaporated. It's used for multiple purposes like making toys, making decorative material, and making smooth surfaces. For example, false ceiling, etc., are quite famously made from plaster of Paris. There is one more point that I would like to say in here is that the water of crystallization. So it is actually the fixed number of water molecules that is present in one formula unit of a salt. What do we mean by formula unit? Is the final representation of a salt. For example, the copper sulfate, the final representation is CuSO4 5H2O, which is blue in color. So in one formula unit of salt, which is CuSO4 5H2O, we have 5 units of H2O being produced, and hence it also has 5 water of crystallizations with it. So this is the explanation for all the 6 products. Now quickly to look at these 6 products, we started with um, sodium hydroxide, and then we looked at bleaching powder. That second, third, and fourth is baking soda and washing soda, and fifth and sixth is gypsum and plaster of Paris. So this actually covers the entire chapter of acids, bases, and salts. And I have given you all the major important points that you should remember for your exam coming up. Yeah, and the way that yeah, the points are written in this presentation, if you are able to really represent it in the same manner, you will find that you would be able to get in the right marks, at all of the questions. So if you feel that there is any point that you need to really relook at, please go through this presentation once again. You can anytime rewind this video and YouTube, and if you have any doubts, you have any questions, you can always reach out to me, either through WhatsApp, or you can post a comment in the YouTube video itself, and I'll try and answer them as early as possible. So this is the presentation for the acid, bases, and salts. So I'm just going to pause this presentation here now, and in another minute I'm going to pause here for a minute. So if you guys need to have a quick minute's break, you can have that. And we will be looking at the next presentation, which is periodic classifications, in the next minute. Let's take a break here for a minute or so, and I'll see you back in another minute or two with periodic classification of elements. See you shortly there. Keep the video on for the same YouTube channel. Yes, and there we are. Let's begin with periodic classification of elements. Yeah. So this is the fifth chapter of our syllabus, and we'll be looking at all the major important factors of all the points that are necessary to be remembered in this chapter. We'll also look at how do we really write the answers and solutions for the this chapter, and what can we make best out of these the questions that are given on this particular chapter. So let's understand this chapter one by one. So this chapter actually starts with the history of periodic table and why is there a need to classify periodic table. So here's what we have as the chapter begins. We know that the classification of the elements is basically arranging of elements into different groups on the basis of similarities in their properties and uh, you know uh, and also depending on their physical and chemical both of these properties. The second thing that the classification actually does is similar elements are put into the same groups, and therefore it makes the study of elements easier. So this is the need of classification. So if you have a typical question as to why do we have to have periodic classification, the reason for that is to study the elements easily, or to study the elements in a form that is comprehensible. It becomes easy because there are almost 114 different elements that the textbook mentions. So how would we really deal with the properties and all the different kinds of chemical and physical attributes that these elements have? And for that we need classification to go forward. So that's where we come in for classification. Now, the chapter very next deals with what is the history of this classification, how did it really began, and what did the early attempts do about this classification. So we know that the earliest attempt to classify elements, which were known then, which were only about 30 of them, was only into two groups, okay, which was firstly metals and non-metals, okay. And the properties of metals and non-metals were broadly known. For example, everyone knew about iron, copper, zinc, which were very common metals in those days. And non-metals like most of them were gaseous, of course. So smoke was known, fumes were known. So some amount of idea was there on the non-metals part. Now, but of course, whenever you talk about metals and non-metals, the very position of metalloids becomes pretty unknown, right? So there was always a defect in just calling elements as metals and non-metals, and now we know that there are much more complexities that are involved, even inside metals or non-metals per se. So in so later on, it came up that metalloids are only those compounds which have properties of both metals and non-metals. To be told like a an umbrella thing for all the elements which showed the properties of metals and non-metals both. Now, the one of the first attempts that was made was by Dobrinair. So, what Dobrinair did was basically he put in elements in a set of three elements per each. So, he made, for example, lithium, sodium, potassium, calcium, strontium, barium, so on and so forth. And he said that the atomic mass, please note, it is the atomic mass, because till modern periodic table, no one was talking about the atomic number. It was mostly you brought in first the atomic number. So till then, everyone's talking only about the atomic mass. And Dobrinair said that the atomic mass of the central element is basically the average of the other two. So for example, here we have 39 plus 6.9 divided by 2, which is nothing but 45.9 almost. So approximately equal to 46. Okay, not really perfect, but approximately equal to 46. And you'll realize that the atomic mass of the central element is 23. If you really go strictly by the measure, the central element's atomic weight should have been 22.95, which is very close to 23. So Dobrinair was successful in doing some of these classifications by putting them as triads. He called them as triads because, of course, of three elements. Because it was made of three elements, he called them as triads. And he gave a couple of triads. It is very essential that you need to know at least minimum two triads by heart. So lithium, sodium, and potassium is one that you can remember as 6.9, 23, and 39. The second one is calcium, strontium, barium, again 40.1, 87.6, and 137.3. And you can have chlorine, bromine, and iodine, you can have 39.5, 79.9, and 126.6. So if you really look at the central ones, you'll find that this is 87.6 and it is 88.7. So they're very close to each other. So Dobrynin was successful in whatever elements were known then, to show them that, look, they are very close to each other, and they have pretty much the same atomic masses. So this was the first attempt that is ever recorded, in terms of classifying the elements that we had known so far. The Right now the second attempt was made by Newland, okay, and Newland basically said that we have elements classified in octaves. Now, when we say octaves, please note that there are only 7 columns. Okay, people sometimes end up writing 8, so you'll find that this is 1, this is 2, this is 3, 4, 5, 6, and 6 and 7. So you'll find that Newland spoke about octaves, and he really said that octave means the eighth element will be similar to the first element, not the ninth. Okay, so eighth elements, like in Saregama Padanisa, you have sa, which was very similar to the initial sa. We say that it's going to the next pitch. So Newland classified all the elements in terms of eight, and you see in those days octet was just, the idea of octet was just coming up. Pauling was the first guy to really give this idea of octet. So and in fact, noble gases were not pretty much known. So there was no noble gas known. It was almost at the end of the 18th century that the first noble gas was found out. So in Newland's time, somehow this 8 number was coming out to be very magical, because everyone was just contemplating, why is it that it's not 2, not 6, but eighth element is being very similar to the first one. But somehow it was just appearing because their properties were same. For example, the property of hydrogen, fluorine, chlorine turned out to be the same. Having said this, there were a lot of discrepancies in what Newland suggested. So Newland's classification is, if you arrange the elements in increasing order of atomic masses into groups of 8 elements, okay, then the eighth element always will be equal to the first. Okay, so he called them as octaves, like notes of music. Okay, he found that when the elements are arranged in equal, in octaves, then they have similar properties, right? So every eighth element will have the similar properties. Now there were some defects of this classification. Okay, so what are those defects? The defects were these. So you had all the known elements, were basically were not put into this, because that we know today were not put, because these elements were not discovered by his time, and therefore these elements could not be put into the Newland's system. Okay. Secondly, some elements having different properties were getting into the same row as someone whom they were not related to. For example, cobalt and nickel. So you see this cobalt and nickel. Now we all know that this would be a very great system till calcium. Okay, because after calcium, the electronic configuration changes, and it's no more octet, right? So then we now know that it is 2, 8, 18, 32, so on and so forth. So 8 was very comfortable till almost till calcium. Okay, after that, even for example, chromium and thallium, manganese and phosphorus, you can see there is a error here, and there's also error with sulfur and iron. Okay, so post calcium, everything which is 20, atomic number 20, everything was good, but after atomic number 20, everything started falling apart. So elements which had the same properties were in different groups, or elements which were in the same group had different properties. So this was a drawback, the major two defects in Newland's octave. And then came our most important contributor to the periodic table, who actually really did a commendable job at understanding what periodic tables could look like. Although his periodic table was also discarded, but he still has a lion's share in terms of what we understand in classifying periodic table. So Mendeleev was the person who did this, and he said that the properties of elements are periodic functions of their atomic masses. So please note, he was still thinking that atomic masses is the fundamental function which would define the properties of atoms. Okay, so what he did do is that he made a table, and he put in columns and periods inside this table. So he actually everything that you have in a as a column were called as groups. So he was the first who actually could term out groups as such. Okay, In fact, he was also very comfortably doing A and B partition of each group, just some in places where he was not very comfortable. So he was the one who gave groups, and all the rows, rows are all the horizontal lines. To all the rows, he started calling as periods, okay? Because it was like a periodic function, right? Like mathematical periodic function. The properties, repeated, and therefore he started calling them as periods after an entire cycle. The lithium had the same properties as hydrogen, so that made sense for calling them as periods. So Mendeleev was the first one who actually gave a table, and you'll see that he was able to put in a lot of elements that were known till that time. But there are of course drawbacks to this as well. You will find that most of the elements are suited. Lithium, sodium, potassium. Now suddenly copper, rubidium, and silver started coming into the first group. Now you see that therefore he also started doing A and B as such. So you'll find that he put in A potassium, whereas in B he put copper. In A again he was putting rubidium, which is again of course group 1 now that we know of in modern periodic table. But in B he started putting it up as copper and silver and gold. Okay, so he did do A and B classifications as such, and he did classify them. So here's a question. He says Mendeleev's table did not have space for undiscovered elements considered a limitation. Well, no, because see, what is undiscovered is unknown. So what is unknown, it's we cannot really speak about it. So I wouldn't recommend to say that it did not have space to put in undiscovered elements to be put in as a limitation. Maybe not. We should not really consider it that way. Okay, so that's Mendeleev's period table. That was a question from Kritika. Okay. What is the difference between A and B? Currently, the difference between A and B in modern periodic table is that A are all of those groups where the electron is added into the outermost shell only, whereas B is all of those groups where electrons are added into inner shells while writing electronic configuration. So that's the current difference. In those days, Mendeleev's differentiation of A and B was mostly in terms of their properties. So the properties of all A elements were different from the properties of B elements, and therefore he had them written separately, in the same. Having said that, he involved them in the same group because he was trying to derive from Newland's octave rules, as well as they all look like metals, and if he did not really follow the octave path, then writing a configuration or writing the table in some other format was even tougher. So he maintained the octave, Newland's octave, but at the same point of time, he realized that in the same group there are not everyone who was having the same properties, and therefore he started putting them as A and B. Today we know that A and B actually comes from the fact that A are all of those groups where the new electron that's coming in goes to the outermost shell, whereas B are all of those groups where the new electron that is coming in actually goes to the penultimate shell, that is, or the inner shells, if not penultimate, in the inner shells. So that's Mendeleev's periodic table. Now, Mendeleev's periodic table, he mostly classified elements in increasing order of atomic masses, that we've seen, and also in the similarities of their properties. Now, he also, gave the formula of all the oxides and hydrides formed by these elements based on their classification. This was one of the very good steps that he did. He actually was able to predict the oxides and hydrides and their properties also based just on their positions. So we know that Mendeleev had done a couple of very bold steps. For example, not only predicting the properties, but also saying that there are certain elements which should be present, but we have not yet found them, and he predicted those elements. So now Mendeleev's table actually simply had 6 horizontal rows and 8 vertical rows called as groups. Okay, so you will see that these horizontal rows that Mendeleev had is what we started calling as periods, and he gave the name periods. And the 8 vertical rows that we mentioned is what he gave the rows as the name groups. And then he also put in subgroups of A and B, as we just said a few minutes ago. In fact, in the 8 group there were 3 rows, but he never mentioned any A B for them, because all the properties were more or less the same. So he did not bifurcate the group 8th group into A and B, but he did for the other 7. Now elements having similar properties were now being placed very well, and he was quite successful. But unfortunately, because his very fundamental assumption of atomic masses was not correct, he was not really good at putting the entire table. In fact, he left blank spaces in the table to accommodate elements to be discovered in future. Okay, so just to again bring up Kritika's point, he actually did keep in spaces if there were any metals to be discovered, especially the ones that he knew was surely to be there, especially in the crowded part of the periodic table. Okay, so this is a quick look at Mendeleev's positives. Let's understand what happened to his periodic table and what were his merits and demerits. So the merits of periodic tables was he actually elements were classified on a more fundamental basis. Okay, on their atomic masses and properties. So this is one of the properties of Mendeleev's periodic table. Again, he actually left spaces vacant to accommodate new elements which were to be discovered in future. Uh, then then he also was able to predict the properties of some elements which helped in the discovery of new elements. He the inert gas elements were discovered later, but would also were able to be placed in a separate group without disturbing the table. So these are the four merits that I have I could put together for you. Now the defects of Mendeleev's table, periodic table, or its demerits was that of course the elements were not arranged in increasing order of their atomic masses always. For example, copper, who has a lower atomic mass, was placed before nickel. Sorry, a higher atomic mass was placed before nickel. Similarly, tellurium was placed before iodine, where iodine actually has a lower atomic mass than tellurium. So the strict order of increasing atomic masses was not observed, which is what he claimed to be the fundamental property of his periodic table. Of course, the position of hydrogen was not clear. In fact, even in modern periodic table, hydrogen is never written in group 1. It should ideally be placed outside the group 1 or somewhere else. So he was not aware about this. So he just had put it in group 1 and he moved on. But he shows the properties of both metals as well as non-metals. So its position was not clear. And of course, isotopes can never be put in because the same element has two different masses. Now, how would you put two different masses and the element and its chemical properties being the same in the same row? So there was no place for them. So isotopes was a major culprit, and their position was not clear. So these are the merits and demerits of Mendeleev's periodic table. Okay, and yeah, let's move on to the next, the modern periodic table. Now, if you look at the modern periodic table, I have just written modern, just to show you the modern periodic table. So now we have 18 groups, and if you really see, there are 16 different names for these 18 groups. The central one, actually, the entire three rows are named as 8B. Therefore, there are only 16 different names for the 18 groups. If you really see, all the lower elements, between the periodic table are basically B group elements, and all the higher ones are A group elements. Now, A group elements are all these elements which are, where, as I mentioned to you, electrons are put in the outermost shell, whereas in B group they go to the inner shells. Now, if you really see, the periodic table is based on the atomic numbers. This was one of the most important distinguishing factors between Mendeleev and the modern periodic table. This was brought in by Mosley. So what was Mosley's experiment? Mosley basically radiated all different elements with X-rays, and he found that the frequency of X-ray that is getting absorbed had a relationship with atomic number. And what was the relationship? The square root of the frequency was proportional to the atomic number of the element, and therefore Mosley thought maybe all these years we were thinking about atomic mass being fundamental, it may not be the atomic mass, it may be the atomic number. Let's try with atomic number. He was the one who brought in this idea. And when this idea actually took roots and people started to experiment, they found that actually it was much more beneficial to put it in terms of atomic numbers. Now, let me just show you some more properties of the periodic table. So I've just brought in here different coloration in the periodic table. So you'll find that hydrogen is kept separately, and it's written in a very different color than all the other elements. So hydrogen is kept separately from the entire periodic table. All the yellow ones, light yellow ones that you can see here, are all alkali metals. All the blue ones are alkaline earth metals. Alkali metals because they produce hydroxides when dissolved in water, and alkaline earth metals is because they are also alkalis, but mostly are found in the earth's surface, earth's crust, in terms of ores or minerals, manures, etc. Now, you will also see that these are all the transition elements which are in dark yellow color. small marronish color here. So they are all transition elements, just for your so that you remember. Or the poor metals, and you'll see the poor metals are the ones who also start becoming amphoteric, like aluminum, copper, zinc. They all start becoming amphoteric in nature, neither being very basic, neither being very acidic, something in between. So these are all metals. So these are all poor metals. When we say poor metals, basically we are saying that they don't ideally give you all the properties of metals very strongly, right? So these are all poor metals. And then we have, of course, non metalloids, for example, silicon, arsenic, tellurium, polonium are all metalloids that we know of. Antimony. And all the white ones that we see here are our non-metals. So please note that non-metals are very, very less in number in the periodic table, whereas metals are highly in number. There are a lot of metals. Now, one important thing that we need to remember is the group that is below this periodic table, which is our lanthanides and actinides. So these are our lanthanides, and these are our actinides. And they are named as lanthanides and actinides because they start at 57 and 89. 57 is the element lanthanum, and therefore from 57 towards 71, these are 14 different elements. They are called as lanthanides, and the lower 14 are called as actinides because they start from actinum. So these are and these are also called as inner transition, just for your inner transition or rare earth. Okay, rare earth or inner transition metals. Okay, and of course the red ones are our noble gases. So remember all the positions of all of these. You are expected to have elements remembered till calcium 20. Why does metallic Kritika is asking, why does metallic character increases down the group? We are just in a few minutes going to see, Kritika, all the properties including metallic character, so just be with me till then, and we'll see this in some time. So periodic table is this is the periodic table that you should know about, and the entire periodic table with its classification is put in this one chart. Please remember this chart and understand the table as you go forward. Okay, now okay, now let's go forward. Yeah, now in this table I have tried to show only the differentiation between uh, excuse me, yeah, only the differentiation between metal, non-metal, and metalloids. So if you see, all the light yellow colored substances are metals, and they have a diagonal separation from non-metals. So if you really see excuse me, guys, yeah, if you really see, there's the metals are separated from non-metals through boron, silicon, arsenic, tellurium, antimony. So there is a diagonal wall of separation. All the non-metals are the ones that are seen here, okay, with the light coloration. And of course we know that these are noble gases. So noble gases sometimes also react like giving covalent bonds, very similar to non-metals, but that's a separate group. Now, so these are metals and non-metals and metalloids. Just a classification that I wanted to show you as such. Also I've written AB very separately, differently here. So, one of the periodic tables that I could find from Central Washington University's website. Yeah. Now, let's look at the modern periodic table and its properties. So you will find that the modern periodic table has elements arranged in the increasing order of their atomic number. This order is very important, and in the form of a table having 7 rows. Okay, so the 7 rows is something that is very important. That is called as periods, and 18 vertical rows of elements called as groups. Okay, so the table here is of 7 rows and 18 groups. So 7 periods and 18 groups. Okay, now what are the periods? What are these 17 periods? The first period has only 2 elements and is a very short period. The second has 8 elements and also is a short period. So there is a very short and short. So the first one is very short. The second one is a short. The third one is also short because it also has 8 elements, and which are from sodium till argon and lithium till neon. The fourth is the long period. Okay, so they have 18 elements from potassium to krypton, and the fifth also is a long from rubidium till xenon. The sixth and seventh are very long periods because they also have lanthanides and actinides, another 14 added to 18, which brings the total to 32. But the last one is incomplete, so therefore it ends up only at 28. It goes from cesium till radon, so therefore it's a very long period, and it also goes from francium onwards till the last element. So there are 114, and it's an incomplete period as well, the 28th one. Now, 14 elements of each sixth and seventh period are placed separately at the bottom of the table. I told you that these are also called as inner transition or rare earth metals. And these 14 elements start from lanthanum till I think Lu. They are all called as lanthanides, and from AC till AR, they're all called as actinides. We have seen all of these, in the periodic table. Okay. Now, this is the arrangement of modern periodic table. Now let's look at the groups in some more detail. So you'll see that these 18 groups are divided into 9 main groups. So 1, 2, 3, 4, 5, 6, 7, 8, and 0 group. The groups 1 to 8 have two subgroups, A and B, as we had already seen. And group 8 has 3 rows. Okay, so that's also we have seen pretty well. Now, all of these rows and the 0 group of has 1 row of elements. All the other ones have 1 row of elements each. The A groups are called as normal elements. The B ones are transition elements, and the inner transition elements are lanthanides and actinides. We have seen this. Okay, the yellow ones were represented by the B groups, and the normal light yellow and the bluish ones were normal elements. Now, inside group 1, 1A elements are called as alkali metals. Inside group 2, the group 2A are called as alkaline earth metals. Of course, the 17th one is called as halogens and noble gases. So we have seen all of these again in the periodic table a few minutes ago. Okay, so there are two more questions. There are a few more questions that we have. So Brian is saying, what is the difference between poor metals and metalloids? Very good question. So Brian, the difference between poor metals and metalloids is that poor metals still end up showing more metallic properties. I'll give you an example. If you generally take aluminum oxide, the almost 80% of the times it would be very strongly basic in nature. Okay, but when you use a very strong base like sodium NaOH, okay, if you use NaOH, you will find that it starts showing acidic property to go give sodium aluminate. But if you use a weak base, for example, NH4OH, sodium aluminate, aluminum oxide will not really react with ammonium hydroxide. So therefore, what I'm trying to say is that in most of the situations, they still end up showing metallic properties. But having said that, in some situations, they end up showing basic properties, and therefore they are called as weak metals. Whereas if you look at metalloids have no preference. They have equal preference to metals and non-metals both. For example, silicon oxide, you'll find that silicon oxide would be basic and acidic, both of them, amphoteric in nature. In fact, you'll find that their another major reason is their bonding, the way they form covalent bonds. So silicon oxides would majorly be forming covalent bonds. Whereas AlCl3, you'll find that coordinate covalent bonds are also present. So the difference between poor metals and metalloids is that poor metals still tend to incline more towards metals in their properties. Ruchir is asking, sir, but doesn't lead have a variable valency too? So shouldn't it come under B group? See, it's not just about variable valency. So there are multiple properties that transition elements show. Some of the important properties that transition elements show is that it is a catalyst. It has empty d orbitals or filling d orbitals. So this is a higher chemistry that we know of. Yes, lead does show the variable valencies, but as you come to lead, you will find that its d orbitals are completely full. So therefore it's not taken under the transition element. Transition element ends at the 2B group, which is zinc, cadmium, and mercury. So that's why Ruchir, lead is not considered. The major factor that we generally see is the electronic configuration. So that's the root problem that we have to really understand to classify someone as transition or simply poor metals. Right. So coming back to our discussion here, so we know that noble gases are 18. This is also something that we have seen. Then in a group, all the elements have same number of valence electrons. Pardon me for this gap. I think while presenting, there are gaps that I've been able to notice. Okay. So in any group, you'll find that the number of valence electrons remain the same. In group 1 element, there is 1 valence electron. So the group number actually shows how many valence electrons is present. Similarly, in group 2, the number of valence electrons is 2. In group 3, the number of valence electrons is 3, and so on and so forth. In a period, all the elements have the same number of shells. So this is the two properties that is very important. I repeat these properties. The group number shows how many valence electrons you have, and the period shows how many shells you have. Now, what are the properties of elements in periods and groups? So this is where, for example, Kritika's question about metallic character and all, we will look into that in detail. So we are going to look at a couple of properties. I think about five of them, yes, uh, which are important for you to for the boards. So the first one is the valence electrons. So in a period, the valence electrons actually increases from 1 to 8. Okay, so you will see that the group 1 elements will have valence electrons as 1, and as you end up going till noble gases, the number of valence electrons becomes 8. So this is pretty much understood from the classification of the periodic table. They are a very arrangement of the periodic table. So you see that lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, as you go from lithium till neon, the atomic number increases from 3 to 10. The electronic configuration becomes 2 1 2 2 2 3, so and so forth till 2 8, and you'll find that the number of valence electrons goes from 1 till 8. Okay, so of course the number of shells remains 2 all across. Okay, so therefore, since they are in the same period as we had just seen a few minutes ago, they are in the same period, the number of shells actually remains the same. But you'll see that the number of valence electrons increases. Let me use a different color and show you. The number of valence electrons increases from 1 to 2 to 3, so on and so forth, 4 5 6 7 8. Okay, so that's how electronic configuration can show you the amount of different variation of valence electrons. Now in a certain group, but you will find that the number of valence electrons remains the same. So, for example, take group 1A from hydrogen, lithium, sodium, potassium. The atomic number is 1, 3, 11, 19. The electronic configurations is this. So you'll see that the number of valence electrons is all 1, always 1. But the number of shells increase. Why? Because now we are going through different period. So the number of shells will of course keep on changing. Okay, so this is the valence electrons that we know of. Now let's look at valency. Okay, so when we are looking at valency, a very common mistake between valency and valence electrons that students do is valence electrons is number of electrons that are there in the outermost shell, or what we call as the valence shell. Okay, but valency is number of electrons gained, okay, donated, okay, or shared. Okay, so remember this difference. So valency is after valence electrons, how many electrons you need to gain, or donate or share. Okay, that is valency. It's not the same as valence electrons. Okay, so generally the case should be that valence electrons plus valency should be equal to 8. That's the general case that we should really look at. But apart from that, valency is different from valence electrons. Please do not confuse these two terms. So now we have seen valence electrons. Now how the valency will change. So of course, when we go from lithium to neon, we have valence electrons as 1 2 3 4 5. We just saw that, right? So valence electrons is increasing from 1 to 8. But let's look at the valency. The valency here is +1. So we are just not writing plus and minus signs. We are writing them without the sign. So we have 1 2 3 4, because these 4 electrons will be shared here. Here 3 electrons will be donated. Here the entire process here, there will be donation that will happen, and the entire process here would be gain of electrons. So the valency decreases from 3 to 1 to 0. So you'll realize that the valency actually increases till the central atom, and it again decreases from the central atom going forward. So valency has a very absurd curve, like it increases here and then again it decreases till the center atom. So that's the way that valency changes across a period. So this is the change across a period. But if you look across a group, the valency remains the same, because the number of valence electrons are the same. The valency also remains the same. So across a group, the valency actually is the uh, it remains the same. Okay, so that's a quick note on valency. Now let's come to the next, which is atomic radius. You see, in atomic radius, the atomic radius actually depends on two things. Firstly, it depends on number of shells. So uh, so number of shells means, if the number of shells is increasing, then of course you will have more number of more will be the size of the atom because the radius will increase. So number of shells or number of orbits is what we should really look at. The second thing that we should look at is what is the number of protons and electrons that is attracting each other. Okay, and as this number increases, the attraction increases and therefore the atomic size decreases. This is a very, very important thing. So number of shells increases the atomic size, and number of electrons and protons decreases the atomic size. Okay, now let's look from lithium till neon. Of course, the number of shells are going to remain the same because we are looking at a period right now. So number of shells is going to remain the same. Let me use a smaller pen. Yeah. Now, if you go from 3 to 10, the number of electrons is increasing. The number of protons is also increasing. And therefore, the atomic size actually decreases down this group. So this is the largest. L is the largest and S is the smallest. So fluorine is the smallest. So in a group, the atomic size of the elements increase from top to bottom. The number of shells increases and the distance between. Right. So yeah, this is where it is. Right. So the number, as the nuclear charge, the number of protons increases, so the electrons are put closer to the nucleus and the atomic size actually decreases. So remember this part on the atomic size. Now let's look at the trend in a group. Okay, so we have seen in a period. Now we look in a group. Now in a group, as you go down, the number of shells is increasing. So our first factor is increasing as you go down. So obviously the atomic size should increase. So therefore, remember the atomic size trend. If I have to really put in the periodic table as we always write, the atomic size actually increases this way and it increases downwards. Okay, so that's the trend of atomic size. Okay, now that we have seen atomic size, let's go to understanding how the elements really look like in a periodic table. So you'll see that helium is a very tiny, very small atom. Of course hydrogen is also smaller than that, or more, slightly larger than helium, but not, the difference is not very high. But if you really look at the major other elements, you'll find that our smallest element is neon and smallest reactive element is fluorine. And in fact, fluorine is so small that if you make F minus out of fluorine, it cannot retain the electron and it starts giving up on the electron. So that's the important anomaly that we have in fluorine. So fluorine actually does not have a very high electron gain enthalpy, that which is the energy that is released when electron is gained. Okay, but chlorine and all are pretty comfortable. But if you see, as you go towards the right, the size is decreasing, and as you go down, the size is increasing. This is one table that can show you. So you can, I've written, it's also written here, atomic size decreases and atomic size increases as you go down. So this can help you understand and remember how the variation of atomic size happens. Now, the next is the metallic property. Okay, this is where Kritika's question comes in. So how does the metallic property actually change as we have different metals in the period or in a group? So as per our trend, we'll see firstly in the period, how does it really change? So in the period, you will see that as the atomic size is decreasing, the electrons are held very tightly. Okay, now as the electrons are held very tightly, they cannot be donated, and because they cannot be donated implies that you are no more metals, because the property of metals is that you can donate electrons pretty easily. So sodium, magnesium, aluminum are metals. Silicon ends up being metalloid. These three end up being non-metal, and this ends up being a noble gas. Okay, it does not donate or accept any electron. So metallic property decreases down the group. So the larger ones are to the left and the smaller ones or the least metallic properties towards the right. And this is also because of the atomic size. Please remember about the atomic size. Because the atomic size decreases towards the right, the electrons are held much more strongly and they cannot be donated. And therefore, you will find that the the metallic property actually has decreased. Now let's look at the same trend in group. Now in the group, what happens is that the atomic size is increasing as you go down. So the electrons that are at the outermost shell, they are so far away from the nucleus that the electrons cannot be very strongly attracted towards the nucleus, right? So as you go further away, the electrons cannot be strongly attracted. So now if they are not strongly attracted, anyone can come and take them off. So the electron donating ability will increase as you go down the group. Therefore, you will see that the metallic property increases as you go down the group, as I have shown here in the chart. Okay, so that's the metallic property trend of or electropositive trend of the elements in the periods and groups. And the last property that we need to see today is the electronegative trend of the elements. Okay, so you will find that the non-metallic property actually So as we have keep the trend, firstly we look at the period and then we look at the group. So you will see that across the period, the non-metallic property actually would of course increase, because the metallic property is decreasing. Of course the non-metallic property will increase. Non-metallic property basically means that gain of electrons. Okay, metallic means loss of electrons or giving electrons. Non-metallic means gain of electrons. The electrons can be gained by the element. So as you go towards the non-metals, you'll find that the lot of electrons are gained back, and therefore across the period, the electrons will are gained more ferociously, more rigorously, and therefore the non-metallic character actually increases as with the period. As you go down the group, you'll find that the non-metallic property actually decreases because the size increases. Our very logic remains the same. The nucleus is here, the electron is going further away from the nucleus because of the increase of the shells, so the nucleus cannot attract the electrons back, so all the electrons can be given out. And as the electrons can be given out, the metallic character increases, and as the metallic character increases, of course non-metallic property decreases. So as you go down the group, the non-metallic property actually decreases. Good. So that actually brings us to the end of all the properties of the periodic table, and a quick look at what we have seen in the periodic table. We started with understanding why it is necessary to have classification of elements. Then we also saw what were the earlier attempts or at the classification of these elements. Uh, Okay, so Mehul is saying he still doesn't understand the previous one. I'll just come to that, Mehul, in a minute. So we started this chapter with classification of elements. The one then we also saw the early attempts at the classifications, then where we saw Doberan's triads, Newland's octave, and then we saw Mendeleev's periodic table. What did this table say? What were its merits and demerits? In all of these history, you need to understand what are the postulates, what are its merits, and what are its demerits. After Mendeleev actually came the modern periodic table, which we use currently. I've shared you three versions of modern periodic table. The very first version uh, I have the version where I have just kept the group numbers to show how A and B groups look like. In the second version, I have shown you how hydrogen, alkali metal, alkali earth metal, transition metals, noble gases, poor metals, non-metals are placed. In the third version, I have just shown what is the difference between metals and non-metals and the metalloids. After this, we saw the properties of periodic table as periods and groups. We have seen what different groups are called. At any point of time, if you feel that there is something that you need to revise, you can just rewind this video. You can go back to that particular point and actually look up. Then we are seeing 5 properties of the elements. So the first one we saw was valence electrons. The second we saw was valency. The third was atomic size, and the fourth one we saw metallic character. Mehul wants to know about metallic character, so I'll just quickly again revise this. So metallic character means that how easily can an element donate electron. Okay, can an element donate electron very fast? So when can an electron when can an element donate electron? When the electron is not held by the nucleus. If the electron is very strongly held by the nucleus, it will not be able to donate. So if the atomic size is increasing, the donation becomes easy. The donation becomes easy. You can simply donate the electrons out, and you will be very happy, giving it out. Now, what happens is that as you go down the group, your atomic size is increasing. Therefore, the electron is going further away from the nucleus, further and further away. So as it goes further away, it can be easily donated by the atom, and therefore the metallic property increases. As you go towards the right in the periodic table, the atomic size actually keeps on decreasing. So the electron is coming closer and closer to the nucleus. So as it comes closer to the nucleus, it cannot be easily donated. So as it cannot be easily donated, the metallic property decreases as you go towards the noble gas. What I also recommend is that if you find that something of this, anything that you have not really understood or missed, I would recommend that you can just, pause the video, rewind, look at it as many times as possible and come back, right? So the second last property we saw was metallic character, and the last one we saw was non-metallic character. So this actually completes the entire description and all the properties of metals, periodic classification. One last question that Ruchir has is that why is it called as alkali earth metal? I mean, is there a reason for earth? The major reason for having alkali earth metal is that because most of their ores are found in the earth. For example, you'll never find, let me look at the periodic table. You'll never find lithium, potassium found as ores in the earth. Okay, sodium, lithium not found as ores, but you definitely find calcium as an ore in the earth. For example, dolomite is one. Magnesium is very much found in the earth's crust, in terms of MgO. So we have magnesium pyrites as well, MgS and all. So all of these second group elements are mostly found in the earth in the form of ores or minerals. The first one are rarely found as ores or minerals, and therefore they are not called as alkali earth. They are just simply called as alkalis, whereas the second one are called as alkali earth metals. So that's the major reason to really know about alkali and alkali earth metals, right? Yeah. So this brings us to the end of the chapter 2. And guys, if you have any questions, Ruchi is saying, sir, can you give examples of polyprotic acids and bases? So polyprotic acids is something that has more number of hydrogen atoms. So for example, we have H2SO4, or for that matter H3PO4. So H3PO4 gives three hydrogen atoms, so it is polyprotic. It has three hydrogen atoms that it can give. So that's polyprotic, and bases, for example, ALOH thrice, it gives 3 OH minus, so it is also polyprotic. So anything that is tri or more than tri are polyprotic, or or dibasic or polybasic or polyacidic bases or polybasic acids. So those are the ways that you can actually understand acids and bases in terms of polyprotic and polybasic or polyacidic. Okay. Right. So, right. So, I hope you had a good time, and this. 1 second. Yeah, so you would have all of this entire recording available. Ruchi, 4 is not majorly available. Okay, so there are certain ions that can be 4 or something, but not really commonly known. There are complexes that are there, which are again beyond the scope of our discussion. There are complexes which have even 6 and 8 H plus that are available. Okay, depending on how many Cn minus connect. But again, that's beyond the discussion of today's context. What I would really recommend all of you is to really look at the entire discussion that we have had in the past 2 hours. Write your answers pretty confidently, and make sure that you are able to put them point wise. I would also encourage you to look at the problems that we are posting on the YouTube channel, and also at the past papers. If there are any doubts, you can reach out to me individually, so that we can do a mostly a one-on-one, or we can save everybody's time on that. And I really wish you best, for your upcoming exams. The video of this entire discussion is available on the YouTube. Maybe we would want to break it into two videos for two different chapters, but they will be available on the YouTube whenever you want. And you're most welcome to reach out to any of the faculty to have any discussions. You can always post a comment in the YouTube as well, or reach out on WhatsApp to understand this. I wish you my best, to take this forward, and feel free to connect for your doubts. Okay. So I'm just going to pause the YouTube video here, but I'm available for your doubts any point of time. Okay. Thank you so much. I look forward to having you all, and meeting you. All the very best for your exams. Try writing your paper in utmost confidence. I know that you have everything in you, to crack it in the best form. So take care. Bye bye. And stay connected. Thank you so much. Thank you, everyone. Thank you, Hiya. Thank you, Kritika. Thank you, Brian. Thank you, Ruchir, Anirudh, everyone. Thanks so much. Bye.